over irregular bottoms by David Andrade.
Thank you very much. Well, first let's thank the organizers again. And well, I'm gonna show you the basic result for my PhD thesis and what I've been working since. I'm now a postdoc here at IMPA. So I'm going to talk about water waves over irregular bottoms. So I assume everyone here knows what a water wave is, right? You've been to a pool, bath, whatever. Okay, so you'll know. So from the mathematical point of view, we usually handle waves, a solution of usually a PDE or a set of PDEs that I'm going to call a wave equation. And well, for this talk, I'm going to focus on linear wave equations. So this means that G is a linear operator. So for example, think about the Laplacian and we get the classical wave equation. And I think we all know here how the solutions of the wave equation look. So it's just like an initial disturbance. It travels at constant speed, doesn't change, and well, we can get, we can add more things to the model. But our interest is to model water. So in order to model water, we need some physical assumptions that tells us how the fluid is. So, well, we will assume that the fluid, the flow is rotational and incompressible, so we can use potential theory to describe the flow, which essentially tells us that we have a function phi, which is harmonic inside the domain, and the domain is bounded below by, the seabed or whatever. And, I'm going to impose an impermeability condition so the water stays above, it's not flowing down. And we have some sort of dynamic boundary condition on the, on the surface. Now, this problem as it is, I might be oversimplifying things, but it's actually very difficult. Why? Because the surface itself changes in time, and we're trying to solve a PD on a time-dependent domain, which changes according to the solution we have. So that's very strong coupling, and it's what makes the problem very, very difficult. So we have to simplify it. And the assumption I'm going to make is that the waves have a very small amplitude. So somehow we don't really need the potential on the surface, but we can simply simplify, we just simplify that the water somehow is always still, and there we're taking all the measurements relevant for our model. Okay, and so how do we obtain a wave equation for water waves? Well, we simply consider imagine we have a value of the velocity potential here on this reference level. Then we solve Laplace's equation inside this domain. Now remember that this boundary is always flat, so it's somehow easier. And then we take the vertical velocity of the fluid, and our wave equation simply reduces to this. Second derivative on time of the potential here on the surface equals to, this linear operator. This is all restricted to this free surface. So we don't really need, we don't need to compute the flow inside the fluid body. And so, in few words, the main outcome of my PhD thesis was an algorithm where you give us the topography where you want to model, when you want to study, and we give you a matrix that represents this operator when you are in Fourier space. So that's essentially our main product. And so what I really want to show to all of you is, interesting features that happens when, we consider waves on irregular boundaries that are not counterintuitive, but I think are nice properties. And, when I first studied them, for me were like, I never imagined that we can actually compute that kind of thing and that kind of thing actually happens. So, if one considers, for example, a flat bottom, then there is an closed analytical solution to the whole wave equation, and it looks like this. Look that the initial wave, it disperses, so it creates this tail behind the wavefront. But we really need the computer here, because when the bottom of the fluid channel is not flat, there is no solution. I mean, we need some sort of approximation. In my case, it's going to be a purely numerical, computational solution. And well, so the first thing we tried was, well, this is the water here. The scales are normalized. So this is 1, this is also 1, but you should think that this is like 1, for example, millimeter, and this is, well, these are different scales. On the horizontal, both the horizontal and vertical scales are stretched, so we can have this view. Okay, and well, what we have here is simply a Gaussian wave that moves to the right and interacts with the obstacle. And this process is because, well, the first thing we needed to do was to benchmark our method. So we are computing things right. And well, the way to compare solution was to actually, well, compute with a different technique the same thing and compare, and well, it worked really well. Difference below 1% in every single point. And we have interesting features. For example, we have this dispersive tail, so these waves coming out the wavefront, and we have reflected waves that they occur as the wave passes over the edges of the obstacle. Okay, so next, we wanted to consider, for example, periodic topographies. In this case, our method captured what we wanted, what we expected, and it is called Brach Resonance. And look at this, this wave here, this tail coming here. It looks almost like harmonic tail, right? It looks like it has like a only wavelength, and it's actually, well, twice the wavelength of the obstacle. And that's actually, well, it was a study from the theory that that was actually the case. And this is known as Brach resonance for waves with topography. Here we tried the same thing, but with now the oscillations are faster. And well, we recover exactly the same result. This wave over here has twice the wavelength of the bottom. In this case, the amplitude of the reflected wave is smaller, but this is because the initial wave is a Gaussian, and Gaussians, they usually have smaller energy on these smaller wave components. That is why it's smaller. And well, we're also testing like how far can we reach with our method, how somehow robust is our computation of the matrix that essentially is doing all the trick. So, well, as you can appreciate, for example, the derivative here is getting larger and larger. So, well, from the numerical point of view, these things usually, I mean, this could be an issue, but it works it works good so far. So we decided to go even one step further and consider more oscillations. In this case, well, for the previous one, we had like 5 oscillations per pulse width. Now we have 12. I mean, our simulation worked. And what is interesting about this regime, when the topography varies really, really fast compared to, well, the scale of the wave, is that the wavefield somehow homogenizes in the sense that it doesn't feel these variations whatsoever. Somehow this thing averages, and it feels like as if it were on a constant depth. And of course, the interesting question is, well, this the wave somehow feels it is on a flat bottom, but what is like the right depth that the wave feels? So, well, we can guess many things, but maybe this is like the So in this simulation, we have all the three waves are like, have the same shape, and they begin at the very same place. They're just solutions corresponding to different depths. So the red one, for example, is the solution with this depth, this flat depth, whereas the green one takes this constant depth here on top. And the blue is actually the simulation. And, one interesting feature about the depth is that the speed of propagation is a function of depth. So we have that the speed, as you see, well, it's lying between this depth and this depth, which somehow points out that the homogeneous media that the wave fills is neither this zero mean or this, well, maximum, but is like here in between. And, well, put it again. Well, there is a well-known theory about this, well, in this setting of water waves with rapidly varying obstacles, and, well, we did not research much on the subject. We simply wanted to show that our method is capable of handling these very complex underwater structures. But now, our main objective for, well, studying this method of building operators out of different shapes was to study the case where we have like a three-dimensional fluid domain with essentially an arbitrary topography on the bottom, and see if we can actually model the waves in that regime. So what we really wanted to do from the beginning was this type of situation. So we have a plane wave coming this way. And, well, here there is like some sort of circular obstacle, a mountain. And, well, this is a plot of the level line. So the wave started here, moves in this direction, and the red circle is where the obstacle is. And so as the wave approaches the obstacle, we see like the things we expected to see. So for example, this is like represents like the shallower regions. So the speed of propagation of the wave is smaller. So this is why the waveform somehow bends backwards. It's got like a delay here compared to here. And in this situation, we can actually study from a theoretical point of view this kind of refraction patterns, which involve an equation that gives you these lines that are known as wave rays. And somehow what we know is that the wave follows the rays. So the rays here, they're like focusing. But on these kind of caustics or singularities that appear on the rays, the theory, it's got its limitations. But I mean, this is a numerical simulation, and we know that the level lines should remain, somehow orthogonal to the rays, and, you can appreciate this in this region. And so what happens at the focus is precisely where we saw that the wave focuses. The wave field also focuses on top of here, and the largest peak that was generated is about 60% larger than the initial amplitude of the wave. So it's the topography that is focusing the whole energy of the wave into a single point is what it's trying to do. And well, let's put it again. Here we have some reflections. I always use periodic boundary conditions, so we can use fast Fourier transform all the time. So, well, there is some reflections here from the boundary. And, well, this is the place where the wave field focuses. Well, we have this circular ring over here, so the whole thing, it was like plane wave. Now it's a circular because it focuses, so gravity pushes down and generates these rings. So, well, we have another example here. We just took the same mountain, but now it's upwards. Now it's a hole. So now instead of focusing, we are doing just the opposite, defocusing, or somehow the wave field is diverging. So again, these are the level lines. And so, well, here is a zoom that we can actually see the level lines, and we have like this sequence of peaks where we actually are the regions that correspond to the higher wave energy. And well, they make this divergence pattern. So here we have it again. So this is a reflection. Look at the wavefront bends on the opposite direction because it is deeper. So the wave speeds up, and that's why it bends the other way. And the simulation can go further in time, but then we have all this reflection that, well, mix everything. Well, this is pretty much like the main outcome of our thesis. So it's a numerical method to compute the matrix. So you're able to simulate linear wave equations with that, well, somehow naive equations, double derivative on time equal the operator. And well, there are many other things that we can explore, that we can do with this model. It is very interesting. But recently, we started to study like the same problem, how we model waves, three-dimensional waves in this, well, in this regime. So they are a real surface, but from a different perspective. Here we're just like somehow using the computer, somehow brute force to compute the operator and, well, get everything done. There is, there is another approach, which is to simplify the model equations into somehow simpler equations that are easier to manipulate, but allows us to keep some of these features. So this is what, well, I started this for my PhD thesis, but, well, we just got an equation that looks very messy, very complicated, lots of coefficients, auxiliary functions, and stuff like that. So I've been working on it recently, and now, well, we finally got a much simplified equation. So, well, these are the assumptions behind the simplification. So I'm going to work in this regime, long waves or shallow water. So meaning that compared to the wavelength, the depth is going to be small, so shallow. And also small amplitude waves is small, so the amplitude of the waves is small compared to the depth, the average depth of the fluid. And I'm also going to assume that the topography somehow is one-dimensional, so it doesn't vary on the, well, on the y variable. It depends only on x somehow. And, well, the main trick I used was the conformal mapping theory that I can extend it in this case. And, well, after some simplification, take Taylor expansion, truncate some terms and things like that, I end up with this equation. So, well, it's got a lot of terms, but look at the black ones. This is a wave equation. We have this coefficient m. M is actually a function, and you can think of it as the topography. So you can think that this equation, the solutions to these equations are solutions to a two-dimensional wave equation. but then it has these blue terms that, well, these constants, C2 and C1, are actually very small. And, well, these are like, you can think of this as Laplacians. So these add some dispersion to the model. So it's got like a dispersion correction. And these terms over here, the red ones, they are the nonlinear corrections to the equation. Well, for people specialists in these things, this equation is actually a Benny-Luke equation, not a Boussinesq equation. What I did was to derive a Boussinesq equation, which is a system. But from the Boussinesq equation, you can easily reduce to this Benny-Luke. So I'm just using this one here to explain like the main features that we have in the system. But for numerics, I'm using the system. It doesn't need to be a function.
No, yes, but like a spoke function, or it can be just continuous, like with sharp edges.
Actually, what we do is to use polygons. And I mean, usually one really interesting thing about this approach, so imagine this is the free surface. We use polygons and you can handle topographies like this. So it's not only, I mean, non-differentiable, but it's not even the graph of a function. It can be handled, at least theoretically. It can be done. Yeah, so as long as this topography is far, well, below, it doesn't touch, we can use it. And actually this coefficient is the Jacobian of the conformal mapping on the surface. But, well, as Andrade showed in one of his papers, it looks, this coefficient is like a convolution with a kernel with something that resembles the shape of the topography. So you can really think of this as the topography. All this thing is inside this coefficient. Well, what we have here, so it's again, it is a Gaussian, and there is a step here at 0. It is a step, but it also grows quite large, so it is like up to 0.6, so 60%. What happens? Well, we have these colors because MATLAB scales the colors. And, well, we see that part of the wave dies faster because it is on the deeper region than the other one that it's on the shallower. And, well, this is right now ongoing work, but I am really positive that this is going to bring really nice results because, I mean, we already know the version, I mean, the two-dimensional case, which is like pretty much the work of Andrade, where there are no epsilons. And, well, most of us I think we've encountered this equation in our study, so I think this could be like a good candidate for a generalization to the three-dimensional case. Well, that's it. Thank you very much.